Hello, everyone, and welcome back to the good stuff. This is the AAS Author Channel series on the AAS YouTube. And today I'm very happy to have Josiah Schwab with us. Hi, Josiah.
Hey, Frank.
How you doing today?
I'm doing all right.
Good. Where are you at these days? Well, besides maybe in your house.
That's right. Yeah. So I'm currently based at UC Santa Cruz, where I'm a postdoc, have been for, I guess, about 4 years now. And yeah, I'm sitting at home, and you can see it's a nice sunny day in
A nice sunny
California.
day
So
in Santa
no
Cruz.
complaints.
It's a nice sunny day in Arizona too, but I'm not opening up my blinds because of the weather. So what do you like to do for research?
Yeah, so my research mostly is concerned with white dwarfs and binary systems. So I'm interested in accreting white dwarfs and in merging white dwarfs and in kind of connections between white dwarf binaries and things like supernovae or the formation of unusual kinds of stars.
Cool.
Yeah.
Very cool. Speaking of, we're going to be talking about one of those unusual types here. So why don't we go ahead and share the screen, and we will going to do a walkthrough of mixing via thermocompositional convection in hybrid CO neon white dwarfs. And Josiah, take it away.
Yeah, so the kind of bigger picture here is I want to, again, kind of think about what sorts of processes take place in the interiors of white dwarfs and in kind of their evolution. And so there's kind of basic understanding of white dwarfs where the kind of mass of the white dwarf star you get, tells you about the composition with kind of intermediate mass, 0.6 to 1 solar mass white dwarfs being mostly usually carbon-oxygen white dwarfs, and more massive white dwarfs, 1.1 or so and up being oxygen neon white dwarfs. And the way you make an oxygen neon white dwarf is by taking a kind of carbon-oxygen core that's formed in a star and having an off-center carbon ignition where this kind of carbon burning progresses inwards and converts what was a carbon-oxygen core to an oxygen neon one. And something that's been proposed is that that process starts but is not successful. It's not fully successful. And what happens is that the white dwarf kind of that forms is still a carbon-oxygen core, and then it's kind of surrounded by an oxygen neon mantle where this carbon burning process has completed, but due to some process like convective mixing kind of messing up the burning front, you've stopped that and you've left what in this paper then in the title is referred to a hybrid carbon-oxygen neon white dwarf, carbon-oxygen core surrounded by an oxygen neon mantle.
How far out does this oxygen neon, or this carbon burning that moves inward, how far out does that start? Does that start way out near the atmosphere, or is it deeper in?
So usually the kind of ignition point is in some sense about kind of halfway in the white dwarf. So if you're in a kind of solar mass core, the ignition point might be at a half a solar mass.
Okay.
That depends a little on the stellar mass and some other aspects, but in the middle is a halfway decent answer for our purposes here.
Good.
And so one of the reasons then why you're kind of interested in what the composition of the white dwarf is that now if you imagine this white dwarf in a binary system where it's growing and where it's increasing in mass, at some point when that white dwarf kind of grows near the Chandrasekhar mass, where it's kind of the maximum mass of the white dwarf, a little bit before that, you typically grow to kind of central densities where you start doing some kind of nuclear reactions. And you might be doing carbon burning. If you have a carbon oxygen white dwarf, you just may get to densities where you start doing carbon fusion and begin kind of core convective carbon burning. And that's a kind of standard pathway towards a type 1a supernova,
right?
Kind of runaway core carbon burning. Another possibility, if you have an oxygen neon composition, is that instead of really getting this energy release from carbon burning, you instead have electron captures on the neon. And that sets in motion kind of a chain of events that lead the white dwarf to collapse and form a neutron star. And so in that sense, what the core composition of the white dwarf is can be really important in understanding what the final outcome is if you put it in a binary system and let it grow.
Okay.
And so that's kind of a big part of the motivation for wanting to understand this sort of thing.
Cool.
And so kind of the setup then is that people propose that, well, maybe these kind of white dwarfs, these hybrid white dwarfs form. And one of the things that then people did was they said, okay, if you do form these hybrid white dwarfs, let's try to understand what the implications would be in terms of type 1a supernovae.
Mm-hmm.
And so, you go through the machinery of putting this in a binary system and doing an evolutionary calculation where you let the white dwarf grow and do kind of central carbon ignition. And then a few groups kind of did explosion models of what does it look like if this kind of hybrid structure white dwarf happens.
Right.
And one of the things that's then kind of different about that versus kind of a normal 1A and that some people saw was that the carbon burning, progressed for a while, and because you still have the carbon oxygen core, but then at some point you kind of ran into an oxygen neon layer, and that kind of changed the properties of the burning relative to what that would be. But something that I pointed out with a colleague in a previous paper led by Jared Brooks in 2017 was that really if you do imagine that you have this oxygen neon mantle on top of a carbon oxygen core, that's not a stable configuration actually. Essentially you have heavy stuff on top of light stuff,
right.
And that wants to mix. And so that if you do think about these kind of white dwarfs forming, there ought to be some mixing processes that destroy this really core mantle structure. And you ought to imagine kind of as these white dwarfs cool that they kind of mix completely. And so you don't necessarily make so at the time you would actually get to something that could undergo a supernova, you might expect the kind of interior composition of the white dwarf to be much more homogeneous than it was at the time when it formed, when it really did have these kind of segregated.
What's the time scale for this kind of mixing?
Yeah, so that's a question, and that's actually part of what this paper tries to answer and understand. And the kind of statement is that the time scale is roughly on the cooling time of the white dwarf, and so you're thinking about something that's maybe kind of millions or tens of millions of years to kind of complete the mixing.
Okay.
So maybe we can start taking a look at some of the figures.
Sure.
I think that might be instructive. So we can start off with figure 1, which just kind of shows the setup here. So this takes a model of one of these carbon oxygen white dwarfs, and this is just showing a little tiny slice in the stellar model. So the x-axis is the mass coordinate. This is like I think this is about a 1.1 solar mass white dwarf. So this is really just a little bit in the center, or a little bit, it's a little bit in the middle.
Right.
And the plot is basically centered on the place where the flame, this carbon burning front, quenched and died. Okay. And so towards the center, the top panel shows the composition. And essentially on the left of this plot, the composition is dominated by carbon oxygen. And on the right of the plot, we're mostly oxygen neon.
Okay.
And so that already kind of tells you that you have, in some senses, a heavy on light situation, because the average mass of the oxygen neon is higher than the average mass of the carbon oxygen. Mm-hmm. But the point that the kind of lower panel wants to make is that this is also heavier in another important way, which is that during carbon burning, there are weak reactions that reduce the electron fraction. That's what YE is here. And so there are also fewer electrons per baryon in the material that burned than in the unburned carbon oxygen. And because when this white dwarf cools, the pressure support really comes from the electrons. If you have a lower YE at the same pressure, you have to have a higher mass density to get that same pressure. And so material that has burned is going to end up having a higher density than material that hasn't, in order to kind of get the same pressure. And that's again telling me that I'm going to sort of end up on this with this sort of heavy on light situation as the white dwarf cools.
Right. So it's a little more neutron rich in the around 0.5 than it is 0.5 solar masses than it is closer in the interior.
Exactly. There's more neutrons there. And initially, this is perfectly happy to be stable. And the reason it's happy to be stable is the stuff that burned is hot, and so it's actually less dense because it's hot and buoyant. And now then the question is, as it cools and that stabilizing temperature gradient vanishes, what's going to happen, and what are the mixing processes like? And we can kind of, we can take a look at figure 2 because this will sort of show the cooling. So now again, we're looking at this same little slice off center in the white dwarf. X-axis is the same here. And the top panel is showing the temperature and at a few different times. And you can see again, the temperature is hotter on the right than on the left. And also, as a function of time, and this shows 3 early time snapshots, the temperature is both decreasing and becoming somewhat shallower in slope. So overall, I'm cooling at this point largely through neutrinos. This is still pretty early in the evolution, and so the cooling is neutrinos because I'm also still pretty hot. You can see here the hot part's 310 to the 8 Kelvin. And also, I'm beginning to kind of flatten the temperature gradient a little bit as electron conduction begins to try to smooth that out. So there's also energy transport moving stuff around.
Okay.
And then the bottom panel shows what's essentially called the density ratio. And again, this is back to this idea of, is this really kind of heavy on light? And this is taking also into account the kind of stabilization from the temperature. And the kind of minimum density ratio here lines up basically with where the composition is switching from oxygen neon to carbon oxygen. So that's really, this dip is compositionally driven here. And as a function of time, the density ratio is falling. And when it falls below 1, which is just the orange dashed line has just kissed that, and the green dotted line is now below that. That indicates that convection, we're now unstable to convection, and that kind of overturning convection is able to begin.
So when you say the density ratio, that's the density of the material compared to what other density? I mean, what two densities are we comparing here?
We're sort of comparing the density the density that you actually have to the density that you would have if you were kind of neutrally stratified.
Got it. I'm with you.
Yeah. So this is, and in terms of what that actually means in the stellar evolution models, that's defined in one of the equations here. I don't know that it's worth taking a look at, but the important really takeaway is again that once that falls below 1, I know the model wants to become convective.
What's that fun spike out at about 0.55 solar masses?
That's a good question. I actually don't know what, off the top of my head, I don't know what that vertical line is.
Okay, fine.
Yeah. I don't think there's anything particularly special there, so yeah, I'm not quite sure.
Okay.
And so we can take this in a stellar evolution model, and both these figures 1 and 2 that we looked at were generated using the MESA stellar evolution code, which is a piece of software that I work on. And as it cools, MESA indicates that this object wants to become convective. But then once you do let it become convective, you often start to have numerical problems due to the way that kind of stellar evolution codes like MESA treat convection, which is essentially convection is something that is on or off. And kind of one of the issues here is that because the composition is playing a big role in the kind of convection, numerically you can have issues where you are convective, so you flip the convective flag on in your code, and that causes mixing that changes the composition. Yep. And also changes the temperature gradient, and that happens essentially instantaneously, kind of in your time step. So you take a time step, and then in the next time step, because you've changed the temperature gradient and the composition gradients, you don't want to be convective anymore. And so you stop. But then the next time step, after things have adjusted a little bit, you want to become convective again. And so in this previous paper, if we just ran MESA and let it go, we saw a huge amount of kind of flip-flopping where little zones were going back and forth, and it was very difficult to follow numerically. And so the kind of approximation we made instead was we said we're really actually most interested in the compositional mixing. We really want to know, again, is this going to cause the oxygen neon and the carbon oxygen to kind of mix and be homogenized? Okay. So we're just not going to let convection change the temperature gradient. So normally you would say when I'm convective, I'll switch to having an adiabatic temperature gradient. And here we said we're just going to leave the temperature gradient alone and just just let it change the abundance. And we know that's not necessarily a great approximation. We would expect convection to change the energy transport and change the temperature. But we're going to do this for numerical expediency. And then so part of the point of this paper is we're going to take a setup inspired by these MESA models, and we're really going to do a kind of a fluid equations calculation where this kind of convections flipping on and off isn't an issue. And we're going to see how well our approximation did.
Okay. All right.
Let's see. So we can keep going down. So yeah, equation 3 there describes, which is up just a little bit.
Oh, there we go.
This describes, again, what this density ratio is, just since we're here. Again, it's really telling me about kind of my difference between the temperature gradient I actually have and the kind of neutral temperature gradient.
Okay.
And then relative to this B term, which is telling me how much stabilization or destabilization is my composition gradient giving me. So this is telling me kind of about this competing effect of the fact that I have a stabilizing temperature gradient and a destabilizing composition gradient.
There you go.
So that parameter is kind of capturing that competition.
Cool.
Okay, so yeah, so let's see. So section 3 largely just kind of covers the setup here. And again, we can't do a real kind of stellar evolution model in this fluid calculation. So we're going to instead kind of solve a toy problem. So we're going to solve the fluid equations, but we're going to assume, we're going to make a number of assumptions. And one thing is that we're going to kind of just try to kind of linearize them. And so express everything in terms of kind of a temperature gradient and a temperature and a perturbation around that, a composition gradient and a perturbation around that. And we're going to make kind of rough estimates of sort of what the kind of important parameters are. But we're not really going to use, say, a stellar equation of state. We're going to use a simple equation of state that is approximately similar to the equation of state in the real white dwarf. Yeah, so we're looking at equation 7 where we're saying, you know, we know that we have just about something that looks like an ideal gas of ions plus degenerate electrons that are providing the pressure support. And then we're going to say, okay, we know what that background is, and then we're going to essentially kind of just linearly expand that kind of equation of state in terms of, you know, a small temperature perturbation, a small mean molecular weight perturbation, a small density perturbation. And so this basically goes through the process of our setup, which I think we can mostly skip through. Yes, and so the other thing, yeah, is we're making the approximation, which is maybe not so great. So we're assuming here again that things that are essentially going to stay in pressure equilibrium and that there aren't big pressure changes.
Right.
That's not the kind of size of this region in the star is actually similar-ish to a pressure scale height. So that approximation is not starts to not be great. But really, at the kind of focus in this paper is kind of at a kind of a qualitative level where we feel okay with kind of ignoring that quantitative detail. Because really the question we want to answer is kind of how quickly does this material mix?
Okay.
And so yeah, let's look at figure 3. Because this kind of shows the setup that we have. Yeah. Okay. And so this shows a few different things. So let's actually start with the bottom panel. So this is showing essentially the temperature gradient in our simulation, and this is something that we just guess a parameterized form that changes with time. So there's a kind of a temperature gradient, which is initially very stabilizing. So it's the blue line sloping up. Yep. And then on the cooling time scale, which we just impose as one of the parameters of this simulation, that temperature gradient is going to get flatter and flatter and go down. And again, that's kind of mocking up the sort of cooling behavior we think we actually are seeing in the white dwarf. So that's kind of what's going to drive the fact that this material, which in our initial condition is convectively stable, is going to become convectively unstable because we're removing the temperature gradient that was stabilizing us.
So is this implemented through like a temp energy loss term, or are you doing something at the boundary to slope there?
Yeah, so in this case, what we actually did is we just we wrote down a simple functional form for what we think the temperature gradient is. And in this case, it's really just kind of, there's a baseline temperature gradient plus a very stabilizing temperature gradient that kind of exponentially decays on the cooling time.
Got it.
So the kind of temperature gradient is not self-consistently calculated from, say, something like neutrino cooling rate or something. We're just kind of saying, okay, we're going to put in a cooling rate on a characteristic time scale. And then really the question we want to understand is that also the time scale then that mixing occurs? And so to kind of see the mixing, if we go to the middle panel here, which is mu, which is basically telling us about the composition, we start on the blue line, and the statement is basically that we have a heavier thing, which is where this mu is high, and a lighter thing where this mu is low. And again, this is centered around 0 because we've taken out the mean part. And we're just looking at the perturbation around that. And here I can answer what the large vertical line to the right of the plot is, which is that the kind of setup in this fluids code we're using uses periodic boundary conditions. So we have to, if we have a mean around 0, if something goes up, it has to come back down at some point. So there's kind of a spot over here where because it's periodic, it has to return to its value at the left side of the plot. And what we're going to make sure we do is that we don't run our fluid simulations long enough to run into this spot on the right. If we do get around there and actually hit this kind of area over here, if we had lots of mixing happening over there, then we would say, okay, our simulation, because it has periodic boundary conditions, has really failed to be a good representation of the star, which is of course not periodic.
Not periodic.
And so we'll plan to stay away from there here.
Okay. Seems prudent.
Yep. And then the kind of very top panel here is essentially something about what the density gradient is relative to the kind of stable adiabatic gradient. Yep. And this is somewhat this is kind of similar in concept to the density ratio we looked like earlier. Right. So initially, when this starts out at the blue line, it's below 0 and it's stable. It doesn't want to convect. And then as we remove the stabilizing temperature gradient, this rises and crosses above 0. And once it does that, the hydrodynamics will want to start to convect. And then once the convection starts, convection wants to hold things at something that's basically neutrally stable. And you can see that both the red and green lines here now have kind of flat regions in the center, which indicates that we're seeing convection happening in this kind of region around where the composition gradient was.
But even when the convection gets going, it extends below sort of the neutral boundary line of 0, right? Both the red and the green curve have convection going on.
So you definitely see some mixing, and when we look at the plots, we'll also see that there's kind of two things happening. So there's really what you think of as overturning convection, where you kind of have these big, large-scale, vigorous eddies. That's happening too. But because this is stabilized by composition, you also have kind of double diffusive convection happening. And that double diffusive convection is really kind of what you're seeing on the edges of these plots. And there you have slower mixing driven by small fingers.
Okay.
And in a second, we'll see that. And you can see that then if you look in the same region where it's kind of flat in the top panel, on the middle panel, you see that the composition is also flat. It's flatter. And similarly for the temperature gradient, it's also flatter. And that's indicating again that the convective mixing is changing both the composition gradient and the temperature.
What is the code used for this?
So this is the Pati Code. It's a pseudospectral code, so it's solving a lot of the equations kind of in a Fourier type basis. It's written by Stefan. There's the description of the papers.
Okay.
And so this is a code that my co-author Pascal Corot is quite familiar with, and she really she ran all the Pati calculations here, and kind of did the Pati side of the analysis.
Nice
so yeah, it was very, very nice. She's also at Santa Cruz, so just walked through the redwoods and then figured something out. So we spend a long time kind of discussing the fact that because we have really idealized this problem, we kind of want to try to convince the reader that, okay, we're in most of the same limits that you're in the star. So that the kind of hierarchy of the cooling time scale to the convection time scale to this double diffusive fingering time scale kind of all have the right hierarchy.
Okay.
And so we're kind of careful to try to choose all our parameters such that that's true. And you'll have to believe me that we did, and if not, there's a couple pages that you can read and hopefully convince yourself. But I think it's worth looking at the kind of pretty pictures, which I believe are figure 5. So
monster Rayleigh number 10 to the 29.
Yeah, so this is of course the real problem. We can't that's the Rayleigh number in stars, and we can't get there. We do our best. Here come figure 4.
All
so
right.
This is worth zooming in. So the lines we had looked at in the previous figure were essentially averages of the simulation pictures we're looking at now. Yeah, this is great. So if we look at just the very onset of convection, not much has happened yet. But you can see that there are these little tiny fingers of mixing between the kind of red and blue marked material, where you can kind of think of red as the hotter ash and blue as the cooler fuel. And you can see there's already been a little bit of fingering, but again, the fingering is slow and hasn't really had time to do substantial mixing.
So was the excuse me, was the interface between the red and the blue perturbed numerically, or is this spontaneous generation?
So there's just a little bit of noise to help get this going, so that we don't have to wait all the e-folding times for it to grow. But it is linearly unstable, and so this is what the fingers you're seeing are the nonlinear phase of an instability that we seeded with a little bit of noise. And so now if we go to the kind of next panel over the like one cooling time,
Mm.
now we've really gotten into the phase where the region between the black lines is expected to be kind of convective. And you now see that it does have these kind of large eddies turning over. And you can see that there's a little bit of mixing beyond that, so beyond the black lines.
Yep.
And some of that is kind of convective eddies kind of penetrating beyond the boundary. And if you also kind of look in, you can also see that there's sort of some smaller scale features beyond that. And that's where you're also seeing some more of this kind of double diffusive mixing. And I think that'll become even clearer, in the insets or in some of the later panels. So I like these pictures a lot there.
So this is 3 cooling times in.
Yep. And you can see again, as the cooling time has gone and there's less and less temperature stabilization, the convection zone between the 2 black lines is getting larger and larger. And you can see again, we have these big mixing regions, and then you can see also kind of the zoom ins of structure and mixing kind of past that regions, and the little sort of fingers on the edges of stuff that have been
almost look like Kelvin Helmholtz roll-ups.
Yeah. There's all sorts of little stuff, small scale stuff going on.
Now we're really mixed.
Yeah, now we're really mixed. And now you can also see that if you look at this kind of white line that's now wavy up at the top, that's that interface that was forced to be periodic, on us by being periodic. So you can see now by this kind of 5 cooling times in, we're getting closer to the point where the stuff in the middle is beginning to interact with that. And so that's a sign that it's time to stop believing these simulations.
Right.
Because we're now starting to see the impact of the periodic boundary conditions.
Let's see.
Yeah, so
just to remind me, the total domain here in the vertical direction is about a pressure scale height?
Yeah, that's about right. Again, there's no, since the calculation itself is Boosanesque, there's no pressure scale height, but the kind of picture would be that we're maybe thinking about a pressure scale height sized region.
Oh, by about 5 cooling times, you've covered about a third of the domain.
Yeah, and so the real question we wanted to ask is, in the kind of simple MESA calculations we did, where we just had to kind of force the mixing not to have a thermal effect,
right?
We saw that the mixing region grew on the cooling time. And that was the time scale on which the white dwarf wanted to mix. And now the question is, in this calculation where we're actually including the thermal effects, do we also mix on the cooling time? And you can basically already tell the answer is yes from figure 4, but we made that a little more quantitative in, I believe, figure 5 or 6. Figure 5. So given the fact that we kind of made up this parameterized version of the cooling time, we know what the kind of simplified initial conditions are, you can kind of analytically write down a prediction for what would the size of the convection zone be if I mix on the cooling time. And that's what this black line is. And then the orange and blue lines are basically the size of the convection zone in R2 and 2 of our calculations, where we've also changed kind of the dimensionless fluid numbers that are governing these, trying to moving them closer and closer to the kind of stellar values, although still fall short of what the actual stellar values are.
Right, Prandtl number.
Exactly. So this is telling us essentially about the kind of, So the real kind of Prandtl number is like 10 to the minus 6 or something. So we're still a ways away. But the point is, in both these cases, kind of the prediction of where should the convection zone be as a function of cooling time really kind of does a pretty good job of matching this estimate of mixing occurs on the cooling time. And as we go further in time past that, actually the formally convection size of the convection zone is kind of shrinking a bit. You can see the blue line is trending downwards a bit. And that's reflecting that then we've sort of started wiping out the composition gradient. And there's also this other kind of fingering mixing happening on the sides of convection zone that's becoming more important.
Okay. Okay.
And so at some level, the kind of takeaway from this paper really is then just that in this kind of fluid calculation, we also find again that the mixing is happening on the cooling time, and that says that the kind of simplified treatment we put in the stellar evolution models is probably also roughly okay.
Okay.
And then the picture is, okay, if I do start off with one of these white dwarfs that initially has this kind of stratified core mantle structure on its cooling time scale, and so on, thousands to millions of years, we really ought to expect this to basically mix almost completely.
Which is short in white dwarf.
Yeah, which is short in white dwarf time, and presumably also is again kind of on the fastest time scale that you could possibly imagine, taking one of these white dwarfs and say growing it up to the Chandrasekhar mass and the conditions where you think you might get a supernova. You think that you really ought to have had plenty of time for these interior mixing processes to occur. And so if you want to do this, you really ought to start from models of white dwarfs that have basically mixed completely. And so then there's been some follow-up work by a group doing supernova simulations where then they've said, okay, we previously tried doing this with white dwarfs where at the time of explosion, they had this core mantle structure. Let's do it with something that's actually fully mixed and compare the calculations. And
right.
See what's different.
What did they find? I know it's not your paper, but I'm just curious.
Yeah. So I don't want to. I'm not sure I can give a good one-sentence takeaway, but they do a good job of kind of describing what the differences they see are, and there are some differences in the explosion energy and the kind of properties of the explosion.
Okay.
So it was something that seemed like it was kind of worth incorporating.
Okay, good. Gives yet another source of potential diversity in type 1A.
Right.
There's no shortage of that.
That's right.
Cool. So, so where do we go from here? Given what you published, and where is the community heading? Look in your crystal ball, and where does the community go with respect to these hybrid white dwarfs?
Yeah, so I think there's kind of two aspects of that. So one is to kind of continue to pursue an understanding of what the impact of that sort of thing is for thermonuclear supernovae, to keep saying, okay, let's say I make these white dwarfs, exactly what sort of diversity could be caused by the sort of these different compositions or different formation processes. But I think another kind of way that is going to be maybe interesting to go is to understand, well, what about these hybrid white dwarfs, if they form? What about ones that don't have a close companion, that don't grow, that don't become supernovae, that just cool down and become massive white dwarfs, single massive white dwarfs? Right. What are the signs of the presence of these kind of hybrid white dwarfs in the population of massive white dwarfs?
Right.
And that's somewhere with the Gaia mission, where we've been getting increasing amount of observational data on massive white dwarfs and massive white dwarfs and their cooling.
Cool.
And there may be opportunities to kind of confront this understanding and these sort of predictions for hybrid white dwarfs with observed massive white dwarf populations.
How about pulsations?
Yeah, so there people have used kind of astroseismic signatures to map out the kind of compositional structure in the interiors, and I think there are opportunities here where, again, you would expect the sort of different compositional structure in the interiors to have different astroseismic signatures, and then whether you can find a good massive white dwarf in the instability strip to do this or not is maybe less clear, but I do think there are potential opportunities. And so in terms of the modeling, I think there are also some opportunities to say, okay, we did this paper with Jared Brooks in 2017 and just kind of said, okay, we'll do whatever we need to do for numerical expediency to follow this mixing. Now that we maybe understand a little more about it, there may be opportunities to try to improve that modeling a little bit so that you could make stellar evolution code models in MESA of kind of these cooling hybrid white dwarfs. And then you could, go to town and see, do the astroseismology, do the kind of predictions of if there are signatures that would be interesting to pursue.
Very nice. So the future is bright.
Yeah.
That's always a good thing.
That's right.
All right. Awesome.
Always lots to do.
Definitely. Josiah, thank you so much for walking us through your paper.
All right.
Really appreciate it. And those who would like to reach out and contact Josiah, go ahead and do so. We won't be putting his email coordinates in a YouTube video or in the description below. But if you're in the game, you'll know how to reach out and get him. So that'll be great. All right, everyone. Thank you so much for listening to this installment of the good stuff, the AAS Author Series. Thanks, Josiah. Thanks, everyone.
All right. Thank you, Frank. Have a good day.
Yep. Bye-bye.